I think it's time to get going. Yeah, it's been a while, and we're trying this stuff out on Zoom, and I think I think it should work pretty okay for what we're trying to do in this class. But naturally, there'll be a little learning curve for all of us here because we're changing on the fly, doing the Zoom stuff here. Um, as I mentioned earlier, there is a way you can raise your hand. And so that might be one way to contact me during the lecture if you want to ask a question. Another thing you can do is you can I think you should all be muted right now so that we don't hear the noise of you shuffling papers and stuff. But if you want to ask a question, feel free to unmute yourself and then just kind of interject, saying I have a question. But obviously don't do that tons and tons of times, obviously. But yeah, if you have a question, definitely feel free to ask one. And we'll get better at this type of stuff, I think, naturally as we practice. So it's been a couple weeks since we've talked about this stuff. And I should mention that I've made your written homework assignment, which I've gotten some email about, homework assignment 3 written. I've changed the due date to that. I've given you one additional day. Originally, after the update, I had it due tonight at 11:59, but I'm going to make it tomorrow night at 11:59. I've also had some people ask me about where they turn it in. Homework 3 written is turned in the homework folder. At the very bottom is where the HW3W turn in is on Blackboard. So that you'll be turning it in the very bottom of the homework folder. Take pictures of your written homework and turn it in on a Microsoft Word document or PDF or something like, probably a Word document would be the easiest. Does anyone have any general comments before we get started on things? I'm not saying too much here. Okay. Okay, so can you guys see my screen, by the way? Can you see the curve there? Okay. So let's, first off, I do want someone to try and remind me here. Can someone remind me, what is the formula for a z-score? Does anyone remember the formula for z-score? Anyone remember the formula for a z-score?
It's x minus mu over the standard deviation.
Yep, x minus mu over the standard deviation. So I'll draw that here on my little whiteboard. Let's see, share this thing. Can you see my whiteboard now? Yeah, you should now. Okay, x minus mu over the standard deviation. That is our formula for z. Goodness, iTunes. Okay, so now we have this thing right here. Does anyone remember the name of this curve that's shown right on the screen right now? Anyone remember the name of that curve? The normal distribution or the normal curve? We have talked about this previously, right? This is something we've seen before, the normal curve, normal distribution. And let's just see if you remember, we can divide this up into proportions or probabilities. Does anyone remember the percentage of the normal distribution that is between 0 and negative infinity? So if we took all of the area from this score of 0 right here and shaded it in all over here to the left, does anyone remember the proportion of area or the probability of a score being in this left half of the distribution from 0 all the way to negative infinity? Anyone remember the proportion or percentage or probability? No one's got it here? So let me ask it this way. Is it greater than or less than 100%?
It's less than.
It is less than 100%. Is it less than 75%?
Yes.
Yes, good. Whoever's saying that, I can't see you, but do you have an idea who's saying that? How much percent is in this left side of the distribution exactly?
Wouldn't it just be 50%?
It is exactly 50%. And you can see it visually. It's half of the distribution is over on the left side, and half of the other side of the distribution is on the right side. So the left side has 50% of the area in the distribution over here, and the right side of the distribution has 50% of the area over here as well. And so this is one of the last things we were talking about, is breaking up the normal distribution into percentages. And this is something that we'll be doing a lot more. I believe that's starting next week. We'll be doing a lot more problems where we're calculating percentages of the normal distribution using these scores down here. Does anyone remember this is -2, this is -1, this is 0, 1. What is the name for these type of scores right here? Anyone remember what these things are called?
Isn't it the standard deviation? Like
Those
the
are,
number of
yes, they are the number of standard deviations away from the mean, but does anyone remember the term for those scores themselves? That is like the
Is it a z-score?
Those are all z-scores. And another thing to remember, what z-score corresponds to the mean of a distribution? If we have a given distribution, it is 0. And you can see that right here because we have this distribution, and 0 is the center of the distribution right here. So the center of the distribution is the mean. And when you've converted all the scores in a distribution to z-scores, the center score, the mean of that distribution, will be 0. So that was just a tiny bit of review. So let's move on here. The last thing that we were working on in class was this distribution of sample means activity. Does this ring a bell to anybody? When we had those bags of little coins, and we were reaching into the coins, and you reached, and each coin, each color had a different, they were dollar donations. So the red coins were a $1 donation. The yellow coins were a $2 donation. The green ones were a $3 donation. And the blue ones were a $4 donation. And it was like money donated at a fundraiser. So each coin represented the amount that a person donated at a fundraiser. Looking at these data, can you guys tell me how many people attended or made donations at the fundraiser? Can someone tell me how many people total were at the fundraiser and made donations? 16 people made a $1 donation. 16 people made a $2 donation. 16 people made a $3 donation. 16 people made a $4 donation.
There's 64.
64.
64 is correct. So there's 64 people there, and it's a very simple, it's a made up distribution, but I made it simple so that exactly the same amount of people donated. Here's the distribution. So 16 people donated $1, 16 people $2, 16 people donated $3, and 16 people donated $4. Let's see. Yeah, so here are what you guys did. So this is a reminding, it's been over 2 weeks since you did this, so it's important for you guys to even remember what we did do. We divided you guys up into groups, and each group calculated 10 sample means. And basically what that meant is you reached into the bag and you pulled out a coin, and depending on its color, you wrote down the amount of dollars that coin represented, either $1, $2, $3, or $4. And you did it 5 times, and when you did it 5 times, you then calculated a mean of those 5 numbers. And then you did that 10 total times. So each group calculated 10 sample means, and each of those sample means was composed of, well, someone tell me, I just said it, but I want to make sure you understand. How many scores was each sample mean composed of? 5. I see a person holding up 5, and 5 is the correct answer here. And I want to actually show you, because I took some time and entered all of the means from both of my classes. I teach 2 sections of stats, and for all of those, for both of my classes, I put those sample means into this Google sheet right here. So for instance, this is group number 1 right here, and these are their 10 sample means right here. This number, for instance, 1.8, they reached into the bag 5 times, they added up all 5 scores, divided by 5, and then the number they got was 1.8. And then they did that 10 times, and the numbers are shown right here. I actually want to quickly show you a group. I'm not going to obviously name the people, but I want to quickly show you a group and ask you a question about it. Right here, can you guys see the ones that are in yellow there? You see they have scores of 7.2, 6.6, 6.2, 6.6. Why could these means were not calculated correctly? I believe they forgot to divide by 5. How can you tell, looking at these numbers, how do we know that these means were not calculated correctly? Anyone tell me, how do we know that the possible donations, think about the different values of the possible donations, and then tell me, why do we know that these are incorrectly calculated?
Because you can't have a donation that was over like $4.
Yeah, exactly. These donations of $7.20 right here, that's higher than the biggest donation you can possibly give. You can either give $1, $2, $3, or $4. So it doesn't make sense that the average donation could be $7.20. And so unfortunately for the activity today, I had to exclude these ones in yellow, but everyone else's I did include. And all of the data are shown here, but I have a summary of the data, which is right here. Okay, so here's the summary of the data. Between the two SATS classes, there was 250 sample means. Each one was based on 5 pulls out of the plastic bag. And the mean donation of those, so the mean of the 250 sample means was 2.5, and the standard deviation of the 250 sample means was 0.469, basically 0.47 right there. So now is probably one of the primary purposes of this chapter 6, is to teach you about the central limit theorem. So this is a quite important thing for statistics to understand. And so I'm just going to kind of read it here. For any population with a mean, mu, the distribution of sample means for some sample size n will have a mean of mu and a standard deviation of sigma divided by the square root of n. And then this last part's less important, but it's still there. And that distribution will approach a normal distribution as n gets bigger, as n approaches infinity. So let's see. First off, someone remind me, what was our sample size for our distribution of sample means activity? What was n? Can someone say, what was our sample size in what was n? That is, for each mean that we calculated, how many numbers were we adding together to get that mean?
It was 5.
It was 5. 5 is correct answer. We took 5 numbers, added them up, divided by 5. Each group did that 10 times. So that is what the sample size was. So what I'm showing you right here on the right side, this is our distribution of sample means. This thing over here is our population distribution. So what the population distribution is, this is just, there were 64 people at the party, and we tallied how much of a donation each of those 64 people made. 16 people at the party made a $1 donation, 16 2, 16 3, 16 people made a $4 donation. And up here at the top, the mean donation was $2.50. And the standard deviation of those donations was $1.12 right there. So this is the population distribution right here. Over here is the distribution of sample means. So what we did over here is we took each of those sample means. So we added up, you took the numbers, you randomly pulled 5 out of the bag, you added them together, divide by 5, then we plot that on this graph, and then we did that for 250 sample means because we had 25 groups, each one calculated 10 sample means. So these data right here are 250 sample means that are plotted right here. And one thing to note is that these two distributions actually look different. These are the people at the party, but these are when we took 5 random selections of the donations and then took the mean. this one starts to look like a normal distribution. And the reason this starts to look like a normal distribution is the central limit theorem, which is this thing that's at the top of the screen. The central limit theorem says that the distribution of sample means will approach a normal distribution, which is exactly what we have here. The really, really important thing about the central limit theorem, though, is this exact number right here. Someone tell me, can you guys see this? What is this symbol right here on the top? What does this number right here mean? Or what is that a symbol for? Whoops. What is this a symbol for?
Standard deviation.
That is the symbol for standard deviation right here. And we're dividing by the square root of n. And someone remind me once again, what was n for our activity?
5.
It was 5. And so what I want you to do right now, if you have calculators on your computer or on your phone, or if you have a real calculator, what I want you to do is I want you to take, so this is the population standard deviation, which for us, the standard deviation of the population is this number right here, 1.1803. You can round it if you want. Take that and then divide it by the square root of 5. So take 1.18 and then divide it by the square root of 5, and then tell me what you get once you've done that, all right? 1.18 divided by the square root of 5.
I have a question.
Yeah, go ahead.
Okay, so it's saying that like so the distribution of the sample is going to have a standard deviation over square root of n, but wouldn't the standard deviation just be the standard deviation? I'm confused on why you have to divide it by.
So this is the central limit theorem. Like what we're calculating, the standard deviation is the distribution of sample mean. So I actually did calculate the standard deviation of our distribution of sample means, but the central limit theorem is a prediction. It says if you have a population and then you're going to make a distribution of sample means with some sample size like 5. The standard deviation of that distribution of sample means is going to be this calculation right here. So yes, I did actually calculate. This number right here, 0.47, is the actual standard deviation of the distribution of sample means. But what I want to prove to you is that this central limit theorem actually predicts that. This 0.47 right here is very, very close to the number you're supposed to get when you take 1.18, divide by the square root of 5. And I want us to prove that to ourselves right now. So can someone, it's not exactly the same, but can someone tell me, what do you get when you take 1.18 divided by the square root of 5?
I got 0.50.
Yeah, that's pretty darn close. 0.5, you might have gotten like 0.52 depending on how you rounded. But what I want, so that's exactly it. It's 0.5 or 0.52. And if you notice, the standard deviation that we actually got for the distribution of sample means was pretty darn close to 0.5. So once again, the central limit theorem says the distribution of sample means is going to have a mean, which is the exact same as the original population mean. Someone tell me, is that true or false for us? Was our distribution of sample means, the mean was 2.5, true or false? That is the same as the population mean for us.
True.
Yeah, and so that worked out perfectly. We took those 250 sample means. I took the mean of those 250 means, and it gave me exactly 2.5. So this aspect of the central limit theorem predicted the performance on our task perfectly. Our mean was 2.5. And the standard deviation of our distribution of sample means was also pretty darn close. The central limit theorem predicted that we should have gotten around 0.5 or 0.52, and we got 0.47, which is pretty darn close to what we are actually aiming for. Conceptually, an important thing that you'll want to understand about the central limit theorem is that the bigger the sample size gets, the thinner the distribution of sample means gets. And if you can actually see this here for the population, this is like a thick distribution, it's wide. But as you increase the sample size, as n gets bigger, and you make a distribution of sample means, the variability or the standard deviation, is going to get smaller, which is exactly what you see here. This graph, the distribution of sample means, is relatively thinner than the population distribution, which is relatively wide. That's an important thing that happens with the central limit theorem. The bigger the sample size, the smaller your variability, of the distribution of sample means. Are there any more questions before I move on to the subsequent slide? Look at some people here. Any questions? Okay, moving on then. Okay, so by the way, it's telling me that it might end our meeting in 10 minutes. I don't know if that's true or not. If it does end our meeting, just come right back on and we'll do the meeting again. It's not supposed to do this because it's supposed to be making an exception for the coronavirus stuff. Zoom is supposed to be making it so it won't cut us off. Hopefully it won't. But if it does, just come right back and we'll just start the meeting off from where we left off. Okay, so we have these two types of z-scores then that we can calculate. We've already done this already, and this is what we talked about at the very beginning of class. I asked, what is the formula for z-score? And the formula for z-score that we've talked about so far is z equals x minus mu divided by the standard deviation, which is this thing right here. And you can think of this as this is basically when we're making a z-score for a single score. And you could think of that as n equals 1. But when we're talking about the central limit theorem, this is the important stuff over here. When we're talking about the central limit theorem, this stuff over here is important. The central limit theorem is when you're making a z-score for a sample mean where the sample size for that sample mean is greater than 1. Can someone tell me, how is this z-score formula different than the z-score formula we have been working with before? Structurally, how is this z-score formula different than the one that we talked about at the very beginning of class?
It's using the standard deviation that you calculate using central limit.
Yeah, exactly. It's this thing right here, sigma divided by the square root of n. This comes from the central limit theorem. By the way, the name of this is the standard error. I believe you have a calculation on homework 3 where you use the standard error. Where you have to calculate standard error. But when we're so we can calculate a z-score for a sample mean. That is, for instance, for our distribution, for the activity that we did before spring break, the sample size was 5. And we created this distribution of sample means. And what we can do is we can create a z-score for any possible mean with sample size 5 in that distribution of donations. The way we would create that z-score would be taking whatever that z-score is, or whatever a given x value is, minus the mean. But when we're taking a distribution of sample means with sample size 5, we would take, to calculate the z-score, we would take the original population standard deviation and divide it by the square root of n. And that gives us a new z-score. You have to do this for homework 3, so this is important stuff. So what we're going to, this is a lot of stuff going on here. And so I'm putting on, I'm not going to read about all this here, but I do want you to see this thing called a Z table. So you can click on this takes you to a Google sheet with the Z table on it. I also emailed you one. So I'm going to click on the Z table right here. And this is taking me to the Google sheet. You all have access to this. But this is the really important elements of the Z table, are these numbers right here. So shown along this side right here, these are the z-scores out to the 10th place. And shown along here, these are the 100th places of the z-score. And so what these numbers in the middle are showing is the amount of area to the left of a given z-score. By the way, there's a term from the readings. If you guys have been keeping up with the readings, you might know. Does anyone know the term that's calculating the amount of area to the left? Well, I'm just going to tell you to save time. It is percentile. What these numbers are showing you here are percentiles. They're showing you the amount of area to the left of a given z-score. So let's look at one. Someone remind me, if we have a z-score of 0, how much area should be to the left of that z-score of 0? Could someone tell me how much area should be to the left of a z-score of 0?
50%.
It would be 50%. And so let's verify that using the z-score table. So right here we have 0 right here, and we got to look the 0.00. So we're going to take this, see 0.00 over here, 0.0 right here, and where they connect right here. Do you guys see? What does that say? Someone, I just want to make sure you can see. What does this say right here?
0.5.
Yeah, 0.5. And so what this is showing is that when we have a z-score of 0.00, 50% of the distribution is to the left of that z-score. And so this verifies our guess, our hypothesis about what 50% is to the left of a z-score of 0. So if I give you a z-score of 3.4, so that's a big z-score, should the amount of area to the left of that be greater than 50% or less than 50%? So I'll ask that again. If I give you a big z-score like 3.4, should the amount of area to the left of that z-score, should it be less than 50% or greater than 50%?
Wouldn't it just be 0?
So I'm going to show you on, it wouldn't be 0. The percent, so looking right here, z-score of like 3.4 would be right around here. And what I'm asking you is, what percentage of the distribution would be to the left of that z-score? So a z-score of 3 would be right around here. What percentage of the distribution will be to the left of that? So is that number, that percentage, would it be less than 50% or greater than 50%?
Greater than.
Yes, it would be greater than. I heard one person say greater than. And so let's verify this here. So now this top part of the this top part of the z table is negative z-scores. You can see the negatives right here. And then you can see the 0 again. They show the 0 again. And then these are positive z-scores here. So to get to 3.40, we go all the way to the bottom. Here's 3.4. This is the 0 column. And we can see 99.97% of the distribution is to the left of that z-score. Okay, so now what I want to do is the last few minutes of class here, I want to go over, we're just going to work together 2 of the homework problems. So I normally wouldn't just do the homework problems but I'm making an exception because of the whole working from a long distance thing. And these problems are relevant to the exact things that we've been talking about in class today. So does these problems look familiar to people? They should. So this is problem number 3 up here and problem number 5 up here. The mean, I think I have. So I'm not the mean, because someone just, I don't know if I have the numbers right here in front of me, or I don't know, I do, but I just don't want to open them up and change the picture here. Does anyone have the mean for these 8 numbers right here? Anyone do the homework yet and have the mean of those 8 numbers right there? Yeah, I do have it right here. I just want to see if anyone knows it. What was the mean of those 8 numbers right here?
53.25.
53.25 is correct. By the way, it might cut us off in 40 seconds. If it does, just come right back and we'll continue on. The mean is 53.25. The standard deviation of those 8 numbers was 11.31. The standard deviation is 11.31. And then it asks you to calculate a z-score. So this is just the normal z-score, the normal formula that we've been using for a long time. I'm going to see 5 seconds. It says it's going to cut us off. So I want to see what's going to happen. Yeah, it didn't do it. Okay, good. You guys can still see me. Can you say yes if you can hear me?
Yes.
Yes.
Good. Okay. Yeah, it said it was going to cut us off, but it didn't. So good job, Zoom. Okay. So the z-score. So it asked us to calculate a z-score for the raw score of 65, which I